So welcome everybody, welcome students, faculty, staff, alumni. In case you want to know, Alex Gansmill is in the audience. She's alumni relations. She's right over there. She's got free pens for some pity. So. That's in case you needed to sign the book, Manil. See how well that worked out? And we are gathered here to determine whether the universe can be built using only math, as Professor Manil Suri claims in his book, right? This new book, there's a lot of them on the table over there. I've got a copy over here. The Big Bang of Numbers, How to Build the Universe Using Only Math. We're treating this book as his dissertation, right? Something that many of us know, that you have to have the oral defense of your work. And today he's going to defend it in front of an interdisciplinary faculty panel. And we'll introduce those in just a moment. And the event is sponsored by the College of Natural Mathematical Sciences and UMBC's Honors College. So, because I think at the end, there's actually some refreshments in the back of the room. So, all right, now it's really my pleasure to introduce the participants. I'll start with Manil Suri. He already has his PhD in math from Carnegie Mellon University in Pittsburgh. And if he fails tonight, and that'll be up to both the panel and the audience to make that decision, we're not going to take his degree away, right? So there's no worry that has to take place right there. He joined UMBC in 1983 and is now a distinguished university professor. And while Dr. Suri has a well-established publication record in the field of the finite element method, the unusual thing about him is in that in 2001, he published a novel, The Death of Vishnu, which became an international bestseller. He is the only international bestseller author I know. So, since then, he has published 2 more novels set in India and has won several awards for his fiction, including a Guggenheim. He also received a USM Elkins Professorship to do math outreach work and a UMBC Presidential Teaching Award. He is a former contributing opinion columnist for the New York Times, for whom he has written several articles on mathematics, India, and LGBTQ rights. His new book on mathematics was supported by a Sloan Fellowship. So we'll be seeing a lot of him today. Now to introduce those that will be asking the questions. Right? Dr. Michelle Osaru, there you go, is an associate professor of English and a former director of UMBC's Judaic Studies program. Her areas of specialization include Shakespeare and Renaissance literature, biblical literature, Jewish American literature, dramatic literature, and performance studies. She has extensive experience in professional theater and serves as the resident dramaturg. There you go. There's a new word. I had to look that up today. So, for the award-winning Folger Theater in Washington, D.C., where she has contributed to over 40 productions. While with Manil Suri, she co-authored the play, The Mathematics of Being Human, performed at the National Museum of Mathematics and several other venues in the U.S. and India. And in fact, remember this? I brought the card. I don't know if it's on video somewhere. It would be like a rare gem if you could find that video and see it. It's a wonderful play.
It's actually University of Pittsburgh did a production, so it's on video somewhere.
It's on video somewhere. I recommend it highly. Next, Dr. Praminda Jacob is an associate professor in the Department of Visual Arts and an associate dean of COS. She is an art historian of modern and contemporary art, specializes in the social and political aspects of public visual culture and on the history and theory of the art museum. Her book, Celluloid Deities, The Visual Culture of Cinema and Politics in South India, was published in 2009. A conversation with Manil Suri about this research is available on UMBC in the Loop on YouTube. She holds a PhD in art history from UCLA and was educated in India and the USA. Next, Dr. Kathleen Hoffman is a professor in the Department of Mathematics and Statistics, as well as the Associate Dean in CNMS. See, I don't have a vowel in there, so I can't go just cow, cos, coet, and anything like this. Her research focuses on mathematical models of biological systems and holds affiliate positions in the Department of Biological Sciences here at UMBC, and also the Department of Anatomy and Neurobiology in the University of Maryland School of Medicine. Additionally, Dr. Hoffman has worked in science education, working both within the discipline of mathematics as well as on the interface of the quantitative and life sciences. Dr. Hoffman frequently guest lectures in Dr. Suri's History of Math class, giving a broad overview of the role of women in math throughout history. And finally, Dr. Philip Rouse. Joined UMBC in 1990 after earning a PhD from the Imperial College of Science and Technology and postdoctoral positions at the University of Cambridge and UC Berkeley. He is a professor of physics and has served as dean of CNMS since 2012. Dr. Rouse has been provost and senior vice president for academic affairs at UMBC. His research is mainly in theoretical condensed matter physics, so he should be really well aligned to ask some good questions. Most recently, Dr. Rouse has played a leadership role in research into innovative tech models supporting student success through the HHMI National Experiment in Undergraduate Science Nexus, the NSF Innovation through Institutional Award, which I used to call IQ, the STEM Build Program, AGAP, and there's probably a whole bunch others in there under that title thing. So we welcome the panel here today, and I'm going to go through a little bit of the structure so you know what's going to happen. So next thing that's going to happen on the list is Dr. Manil Suri is going to give us a presentation, which is standard. You give an oral defense, you would give a presentation. And from then, the panel will come forward, and they'll be able to ask questions. There are going to be 2 questions per panelist for the first round, and then we'll go back again for a single question in case there's something else that they need to ask and clean up. After that point, the audience yourselves be invited to ask questions as well. Then maybe we'll send Manil out of the room, which is standard practice, and the panel will confer, and the audience will confer. And we'll come up and decide, does he pass or did he fail? Did he make his case in such a way that you believe it or not, right? And at that point, we'll bring him back in the room. You don't have to leave if you don't want. But and then we'll give them the answers. And then after that, there'll be a reception, some food and drinks at the back of the table, and we have the ability for a book signing. And I love the way they set up the books. Good job. And we remembered a pen, so as we went along. So I give you Dr. Manil Suri.
Thanks, Bill, and thanks to all my panelists. I'm very honored that you're all here. And people in my class, I just want to tell them I'm not going to be wearing this suit and tie. Don't expect that. I'm just doing it because I need all the help I can get. So that's why I'm dressed this way. Yeah, thanks. Oh, I'm muted. Okay. So see, I told you I need all the help I can get. Okay, let me see if that helps. Yes, good. I'm not going to repeat my jokes. Hopefully there's going to be more to come. This talk is, here it is. I was trying to figure out what to put in and what not to put in. And I'm going to give you a little bit of the history of where this project came from. And to do that, I'm going to go back to 1977 when I was a student in the University of Mumbai. And this was, I was a physics major, actually. And there was a professor who talked about a very famous line from mathematics by this mathematician named Kronecker, who said that God gives us the integers, the whole numbers, and everything else is developed by mankind or humankind. And that just means that mathematicians can then use them to do all sorts of things. And then this professor, his name was Huzur Bazar, said that actually I can do better. We don't even need God because humankind can actually make the numbers too. And he proceeded to show us something which was quite amazing. He showed us how you can create the numbers out of nothing. So that's going to be the first thing, since we are talking about creating everything out of nothing. And this is actually a trick of some sort. Anytime you hear about creatio ex nihilo, which means creation out of nothing, there's usually a trick involved. By trick, I mean there's usually an asterisk, right? In physics, you might need a singularity from where everything comes. In religion, you might need a supreme being. And in mathematics, what you need is something called the empty set. Now, a lot of you have probably heard the word set, which just means a collection of objects. You've probably seen Venn diagrams, which represent sets. You can talk about the set of people in this room. You can talk about the set of trees in a garden. But what happens if your set doesn't contain any elements? Let's say there was no one in this room. There were no trees in your garden. Well, then you get something called the empty set. So it's something which doesn't have any elements in it. Set of all truthful politicians, for instance. So you can come up with all sorts of examples like that. And that is the asterisk that mathematicians start with, the empty set. And what you do is you actually equate that to be 0. This is something that has a long history. Zero was invented in South Asia, and people back then, the Indians or people who lived there back then, their religion talked a lot about the void. And some theorists say that, from that idea, out of nothing, they actually created zero. So call this zero, and then you do something else. You now create a set that contains zero. Now, if you look at this set, is this empty, or does it contain something? You will see that if you think about it, this set actually contains the empty set, so it's a little different from what you had before. And what you do is you equate this to be the number 1. So that's how you invent 1. And once you have 1, then you can actually keep doing this. You can now take a set containing 0 and 1. And when you do that, what do you get? Well, you have a set with 2 elements, and that is what you call the number 2. And once you get the hang of this, and this is what happens in math a lot, you start repeating the trick, and you can start developing 3, and then 4, and so on. You can just keep going on. And it's almost like what's happening is after each set, you create another one. You start getting the numbers in order. It's almost like there's a chain reaction that's been set up. And suddenly, what you have is you have all the numbers. And this is what I mean by the Big Bang of numbers, the title of this thesis that I came up with. You can create all these numbers out of nothing. Okay, so what happened? That was back in 77. I actually was so enthralled by this that I actually switched from physics to math and made math my major. And in the intervening years, I came to this country. I was at the university, at Carnegie Mellon University in Pittsburgh, finished my PhD there, came to UMBC. Of course, it didn't look anything like this when I joined. So came here, and then as Dr. Lacour said, I then went up the usual ladder of assistant professor, associate, full professor. And then in 2001, I published a book. And this was a hobby which suddenly became serious, and it was a bestseller. I ended up publishing 2 more books. And as a result of that, I was invited by the New York Times to actually write an article about mathematics. And this piece that I wrote was in 2013, a long time ago. And the idea of this piece was that mathematics is too much about, people think about it as just all about calculation, whereas it's really about ideas. And this article started doing very well. Excuse me. And I kind of followed it. It started rising up on the most emailed list for the day. And it reached the top of that list. And then it kept going. And over the week, it started climbing the most emailed list for the week. And by Saturday, it had reached number 3. And then it was number 2. And I was all set to be most emailed for the week. When what do you know? But the Pope started making all these provocative statements about abortion and gay rights and so on. He came bounding from behind me, and then just leaped over and grabbed my number 1 spot. And you might think I have something against him, not much, not at all. And in fact, I've even sent him a copy of the book. I'm not kidding that, I did. But he is actually a character in my novel because it made me realize that religion is something that is very popular, as is physics, actually. Mathematics, not so much. And so this whole project, and in fact, even my PhD thesis, the one that I'm defending, is really about how to make math, how to do outreach in math, how to make it more interesting for people. So that's what I'm going to be talking about mostly. And this vehicle of trying to build the whole universe through numbers is the way that I decided to attack this problem. So let's see. So that's the book, obviously. But what I did was, to take this motif of religion, I decided I would follow the idea of Genesis, where you have 7 days, and God is supposed to create the universe in 7 days, 6 days, and then the last day is for rest. So I'm following that roughly. And day one is going to be, well, the first thing you do with the numbers is arithmetic. And so day one is arithmetic. And remember, I was a novelist, so I actually wrote this book several times. I wrote it as a novel. Well, actually, I'd even started writing it before the New York Times article, but my publisher had said something like, oh, this is very charming. Not a word you want to hear. No. That means we can't publish this. Try again. So then when the New York Times article came out, then I said, okay, let me try to pull this together in terms of, a novel, since I'm a novelist. So I wrote the whole thing as a novel. And the publisher, again, said, something like, no, I don't think people will buy this. So then I had to rewrite the whole thing again. But what happened is, as nonfiction, that I retained some of the kind of fun things that came from the novel. So the numbers that you've just seen them be born are actually going to be characters. So they're actually things, entities that have, little bits of personality and so on. So some of you will have seen this. Incidentally, I'm actually teaching a class this semester, an honors course based on this book. So I see several people from my class, and they have actually seen some of this and reacted to some of this. So it's been very fulfilling that way. So anyway, the numbers are characters. Reason for doing this is that math, remember, and some of you have probably not seen this, but math, if you ask mathematicians, is really a game. You start with some rules, and then you see where those rules take you. And by making these numbers characters, I was able to have them play games and give you a taste of what that felt like. And what kind of games would numbers play? Well, they would add. They would come up with addition, with multiplication. And these whole numbers, when you add them together or you multiply them, you end up with another whole number. But then these numbers start doing something that's dangerous to them. They start doing subtraction. And 6 minus 4 is fine, but 4 minus 6, there's nowhere to go. There's no number. So suddenly you have all these stuck pairs everywhere in the universe, in this universe you've created. And the only way to get rid of this situation is to start inventing more numbers. So that's when the idea of negative numbers comes up. And then they play more games. They start doing division. More stuff gets stuck. You can divide 6 by 2, but not 2 by 6. Well, how do you cure this? You create even more numbers. You create fractions. Fractions, as we know, their decimals, keep repeating after some point. And then they play other games like square roots, and that leads you to irrational numbers. So here's something interesting. If you start looking at these kinds of numbers, these irrational numbers, how is this going to help you in terms of the universe you're creating? Remember, the whole idea is I'm taking the reader along on this journey, and we're going to create the universe using only numbers, using only math. So where are these irrational numbers going to fit in? How are these going to be helpful? And the first thing that at least mathematicians always say is, hey, this is going to make us be able to do things very precisely. Like if you're looking at the number pi, you can continue calculating it to as many digits as you want, and you can be very precise about something, about everything. Well, it turns out you don't need all that precision. NASA, for example, only uses pi up to about, 15 or 16 digits, and that's enough for everything that they do. If you actually calculated pi to 40 digits, you could basically narrow down everything to the size of a hydrogen atom. And so in some sense, you don't need all that accuracy. The reason this is actually important in the universe we are creating is that it actually gives you an idea of randomness. If you look at pi, we know that there's no real pattern that these things follow, like 0.33333. There's no repetition. So you can actually create some sort of idea of randomness, which will be very useful later on in our universe. So it's not true randomness, because if you know pi, you know what the next number is going to be. It's something called pseudo randomness. But anyway, what I want to point out is that looking at these numbers and looking at math in this way, that you're trying to create things, gives you a different perspective. And that's what I found very entertaining and absorbing as I went through this book. Okay, so what do you think day 2 will be after you've done arithmetic? Anyone? What comes after arithmetic? The two choices are algebra or geometry. And I tried both of them, geometry won. So, and the reason is that geometry is something that is actually inspired by the numbers. If you have numbers, they're kind of in this formless universe. They're entities, remember? They're fighting, they're playing games. You need some order. You need to give them some place to live, some sort of private condo unit in some sense. So we'll see how that works out. So geometry is interesting because it allows me to tie something about this project to art. And this is a famous quote by Kandinsky, the Russian artist, who said that everything starts with a point. He actually used a word that might be closer to a dot. And what he was saying was, anytime you have a pen or a paintbrush and it touches a blank canvas, the first point of contact will be a dot or a point. Point is different. A dot actually has some area, covers some canvas. A point doesn't. A point is just, a location. He has a book that he's written, which is very interesting because the way he thinks about these points is that a whole bunch of them will make a line, and a bunch of lines on this blank canvas will actually cover the whole canvas. So we are actually going to follow the same kind of idea that if you have 2 points, you can join them by a whole bunch of other points. This is actually one of the assumptions that Euclid, the famous mathematician, also made. If you give me 2 points, I can join them by a line segment. Not only that, but Euclid also said that you can then extend this line segment all the way to infinity. Now, this is an assumption he makes, because we can't go around and trying to see if we can actually do things at infinity. We are finite people. So this is one of the things that math is made out of. It's made out of assumptions, also called axioms, which help us build up the subject brick by brick. Not so far from what some of the artists, like Kandinsky, were also trying to do. Build things up, build up art, build up their own worlds brick by brick. So once you have this kind of line, then you can stack these lines together, and what you get is a plane. And once you have a plane, you can stack them together and get, what we call 3D space. And there's some more technicalities that come along the way. But notice you don't have to stop here. I could stack together these 3D spaces that I have, and I could get 4D space. Now, the problem I can't really do that is because we are sort of stuck in 3D, but conceptually, you can always think of that happening. So you can access things that we can't really experience. And then you can keep doing that for higher dimensions. I love this analog of doing this point by point and talking about crocheting. So in crocheting, you can make the analog of a line just by taking knots. And you take a string of them, you can extend it perhaps to infinity, if you had enough material, I guess. You could also make a patch. The problem with that patch is that you have to go zigzag, back and forth, back and forth. So you wouldn't be able to really expand it to infinity. What you could do, however, is you could create a circular one, and then by repeating these circles, you could really create a flat patch that, if you continued, would go on to infinity. Now, if you look at crocheting books, or if you look on the web, I looked at something called spincushions.com from a woman who's somewhere in Australia. You will see that there are very definite instructions on how to make this flat patch. Does anyone crochet here, incidentally? Okay, yes, Sarah from our class, she actually did all this. One day I came to class and she had made these patches and all these other geometries that I'm going to describe. So that's amazing. But here is what the crocheting websites will tell you. They will say that be careful about two problems. First problem is where you're not putting in enough material. When you're making these rings, you're not putting in enough material. What that does is that the patch, instead of being flat, is forced to kind of curl upwards. And it turns out that if you do it correctly, if you do the right rings, you can actually convert this, if you kept going, into a sphere. So what's happening is when you don't put enough material, you're actually basically trying to construct something, a geometry that's closing in on itself. This sphere can also be constructed by looking at the same axioms or assumptions that Euclid made, but saying that, that initial line that materialized between the 2 points, if that had been the arc of a circle instead, you would have been able to complete the whole construction and ended up with a sphere instead. That just shows the flexibility of axioms. If you interpret them in different ways, you can end up with different results. And that's one of the key things about mathematics. Math itself doesn't really say anything about anything. It's completely agnostic. But it can be used in different, can be applied to different situations and give you different results. Also, depending upon how it's developed, you can get completely different mathematical systems. So this is one of them. But let's get to another problem that you can have while crocheting. You put too much material in it. Well, when you put too much material, then what you'll find is that this excess material has to go somewhere. And what it does is it starts creating ruffles around the edges. And this is called ruffling. And if you continued it in a smart way, you would end up with some very amazing shapes. This is an example of hyperbolic geometry, which is sort of the opposite of a sphere. Sphere is very little material, it's trying to close in. Hyperbolic geometry is too much material, so it's creating these extravagant ruffles. This connection was first found by a professor at Cornell, Diana Taimina, and she was actually only a graduate student then. And her professor was talking about this and saying how difficult it is for anyone to really imagine these surfaces, how it was only mathematicians who could really imagine these surfaces. And she said, wait, give me a week and I'll actually crochet this. And sure enough, a week later, she had this amazing object that people could then touch and actually tactile, play with it, experiment with it. So that was amazing. What's really amazing is that this kind of surface appears in things like coral and other life forms. Anytime some organism wants to have a large surface area with very little volume, for example, if it's filtering its food through the surrounding medium, it'll do this. So this is interesting. Corals knew about this mathematics about 500 million years before humans did. So they've been using this all along. So that's kind of fascinating. Okay, so day 3, we kind of know what it is. And at this point, I'm just going to give you, I took several years to write this book. And so as not to go crazy, I was kind of entertaining myself by doing little videos in PowerPoint. So I'm going to show you one of these videos that kind of encapsulates the idea of this day 3. Remember the order in which we created all the numbers, whole numbers, negative numbers, fractions, and so on. You'll see that same order occurring. And then you'll see a way of representing all of that. So let's look at this video. And let me turn up the... Okay, so that's my little algebra video. But it's actually pretty neat because the title from Thus Spake Zarathustra is actually perfect, since algebra is where you actually get a way to convey mathematics. It's actually the part where you start thinking of math as language. Uh, and in my construction of the universe, I was actually at a pretty scary point at this point, because here's the problem. Sure, you can create, all these abstract things like empty space, which is what we did in day two. Empty space, incidentally, is something that you never hear about in religious kinds of contexts. So, how do you actually create anything physical using math? Well, math can create ideas, but can it actually create anything physical? Can it actually cross that barrier? I had to admit that I was kind of stumped by that. Uh, so what I realized was that the key word is building. What does it mean to build something? You think about, all the great builders of the past, someone like Shah Jahan, who built the Taj Mahal. Well, he didn't actually use the chisel. He didn't really put mortar and things like that. He just designed things. He like had a contractor basically who did it. So we are going to actually do the same thing. To get through this day and continue on to further days, we're actually going to get a contractor, and this contractor is going to be nature. Now, whether nature is something you interpret as God or something spiritual, or you interpret it as something scientific, maybe physics, that part we won't worry about. What we will worry about is being able to give nature our commands. We'll instruct her what we want her to do. And this is where algebra comes in, because we can specify now. We can say, these are the specs. This is what I want produced. And so that's where algebra comes in as a language, and as other things too. So moving right along, day 4, well, day 4 is going to be patterns. Math has often been called the science of, or the study of patterns, and this all sorts of patterns in the universe, fractals, this, that, and of course all of these are very exciting and things that I talk about in my book. I'm going to just give you a glance of one thing at one topic from this whole section on patterns, and that is 2 ideas on how mathematicians talk about beauty. Now, if you're going to create the world, we should be able to do everything. So can math speak to the whole idea of beauty? And there are 2 ways that mathematicians attack this problem. One is they talk about the golden ratio. You've probably seen this. There's even a blockbuster movie. Who was in it? What was it called? The Da Vinci Code. I don't know if anyone saw it. I didn't. But that had the golden ratio mixed in. So this ratio was known all the way back in the time of Euclid, but it actually became much more popularized around the 1500s, I think, or whenever Leonardo da Vinci was active, by an Italian by the name of Luca Pacioli, who wrote a book called The Divine Proportion, and said that this golden ratio is supposed to be particularly pleasing to humans. It's particularly harmonious. And he was actually the math tutor to Leonardo da Vinci. And Leonardo da Vinci used the golden ratio. He made 60 drawings for this book by Pacioli on the golden ratio. So Da Vinci was definitely aware of this. So the golden ratio is often people say that, that Leonardo actually framed the features of the Mona Lisa to fit this ratio. So there's different thoughts about that. But that's one way that people talk about beauty. Incidentally, I was looking up different things on the web, and there are actually papers written by plastic surgeons on using this ratio to figure out what the best placement of your new nose or whatever is going to be, so that it's nicely harmonious. Now, whether that makes sense or not, there are big ads on the web that you can say, we use the golden ratio, things like that. So the other idea that speaks to beauty that mathematicians come up with is symmetry. And what you do is you look at different figures and say, hey, how symmetric are these? For example, you can talk about how many ways can you flip a figure so that it remains the same after flipping. And what I mean is that if you look at the rectangle, it can be flipped in 2 ways, and it remains the same when you flip it those ways. Triangle, equilateral triangle, there are 3 such axes. A square has 1, 2, 3, 4, 5, how many is that? 2, 4 of them. So the square, you would conclude, is more symmetric than the other 2. And if you're equating symmetry with beauty, which incidentally, a mathematician by the name of George Birkhoff did in the 1930s. He wrote a huge text talking about how the more symmetry you have, the more beautiful something is. So the hexagon would be more beautiful than the square. And the most beautiful of all, I guess, would be the circle. If you think about it, you can draw any line through the center, and you can flip it, and it'll remain the same. So it has a lot of symmetry. Well, the Mona Lisa is a 0. She has no axes of symmetry, not even bilateral symmetry. That's what is supposed to be one of the supposed features of beauty. Well, so she has no axes of symmetry. So we're going to fix that. We're mathematicians. We can do better than that. So we're going to improve upon what Leonardo did. So let's see what we can do about her symmetry. So let's see what we can do. First of all, I'm just going to make her symmetric. Well, okay, so that's not so good. So and the problem is she's lost her, the ratio that she had. So let's just stretch her out a little. Okay, so now she's back, but still not very good. And what can we do? Well, let's try to increase her symmetry. That's what George Birkhoff said. Keep increasing her symmetry. So what I'll do is, okay, that's too long. I admit it. So what I'm going to do is I'm going to resize her. Okay. Still, you would say maybe keep tinkering with this. Okay. So let's remember the thing about the diagonals. That's the problem. She's not symmetric about the diagonals. So what I'm going to do is I'm just going to take a piece of her like this, and then I'll just reproduce it, 4 copies, and then bring them all together. Okay, that's definitely going the wrong way. There's no face left. And the reason for that was we didn't do it the right way. This is the way we should do it. We'll take that top part. Okay. So maybe not. Maybe not. She looks like something really angry now, like soccer ball or something. Okay, so what can we do? More symmetry. Let's not, let's always respect our material. Let's go with more symmetry. What I'll do is I'll scrunch her up a bit, and then I'll reproduce her. Okay, well, now you can twirl her around. So that's kind of nice. But why stop with 6? Why not, or 8, whatever I did. I'm going to do more copies, and she's actually getting kind of nice looking now. And if you keep going this way, you make really fine copies, and then you kind of join them all together. What you'll get is a circle, and you can really twirl that around. So this actually gives us 2 different ways that mathematics comes up with beauty. There's the aesthetic of the original Mona Lisa, and then this one with the circle. Now, I want to tell you, people say math, people take math classes and they never see what the application of math is. So I'm going to actually apply this right away and show you that math is useful for something. We just had the election. So what if I use this on, let's say, these 2 characters and try to see how I can, chances are everyone in this audience would probably be extremely scared or hate or whatever one of these 2. So let's see what symmetry does to them. So this is what happens first. And this is the scary part. You have to get through this scary part. So you have to make them more symmetric. And then finally, what you end up with is something so harmless that you could actually hang it up on your wall. So that's what you end up with. And so both of these are kind of harmless in this way. Okay, so that's the day 4. I'm going to go very quickly now. Day 5 is going to be physics. And remember I talked about axioms? So this was, at this point, when I was trying to do physics, I said, I've already written several hundred pages. If I try to fit in all of physics in here, first of all, I don't know much of it. And secondly, that's going to be thousands and thousands of pages. I don't think my publisher would be very thrilled with that. So what I said is, how can we bring out the connection of math and physics? And luckily, there was a mathematician by the name of Hilbert, who in 1900 came up with 23 problems that were open problems in math. Problem number 6 was make everything in physics be axiomatic. So all the more computational areas of physics, make it axiomatic. Start with axioms, start with basic assumptions, and try to build up all of physics. So he didn't say exactly how to do that, but he started the ball rolling, and since then people have been doing that. And so I'm going to just imagine that Hilbert's helpers have run their wand over this and somehow managed to do this. And what I mean by that is, if you look at physics, there's actually at the base certain axioms, certain assumptions that you have to make. For example, if you're combining two particles with mass m1 and m2, then the total mass, the new mass, is going to be their sum. So some sort of conservation of mass. So I'm not going to talk more about that. I will say one thing about this picture, which you've probably seen. This was something that, remember, we talked about when we were doing geometry, how you can actually create curved versions of geometry, the hyperboloid and the sphere. You can actually do 3D versions of this too. We talked about the ruffling and so on. Well, you can kind of do that, but it's hard to really put your mind around it. However, what I think many people in this audience know is that Albert Einstein, many years after these type of curved geometries were discovered, used them in his theory of relativity, of general relativity. And what he basically posited was that space-time is actually curved. It's not flat, but it's curved. And here is the interesting thing. This idea of curved geometry was done by mathematicians who were looking at completely abstract things. They weren't thinking about coral. They weren't thinking about space-time. They weren't thinking that someone, 100 years later would use their stuff. They were just starting with some rules and trying to play this game. How is it that this stuff turned out to be so useful so long in the future? And this happens over and over again. If you think about circles and ellipses, these were invented by the Greeks. Well, Kepler, hundreds of years later, used these and showed that this was exactly the path followed by planets. Group theory, which talked about symmetries, turned out many years later to be exactly what is needed in quantum physics. And there's all sorts of examples like that, where things were created abstractly, and then they happened to be exactly what was needed. So this shows what I've been trying to say in this whole talk and in my book, that the idea, the driving force behind the universe is indeed mathematical. And nature basically uses those ideas, tries to make them physical, doesn't get it quite right, but tries her best. And one of the key things that works a lot in this mixture is infinity. Even though it's something that we never really encounter, it's really behind the scenes, like a godfather, invisible godfather. I call it the godfather of numbers. That's playing a role that we don't even know of several times, but it's deeply embedded in all the mathematics that basically is at the center of the universe. So the final slide is day 7, and that's supposed to be the day of rest. And this is where something called emergence occurs. Throughout this book, there are what are called input-output algorithms that you do some input, you do something to it, you get an output, you plug that back in, and then you keep going. Very simple things that involve only x squared or something, but which lead to extremely complex and extremely amazing patterns being formed and other things being formed. So in this day, think of it that all these processes have been set in motion automatically, and that somehow these are going to continue in the background and are going to create everything. While the creator, us, we, nature, can take a rest. And I'll give you one example of this magical kind of emergence that occurs. And this is perhaps my favorite example. It's about how ants optimize their path to food. It's a very simple idea that is used, very simple algorithm. If they find food, there are probably several different paths that lead to the food back to their anthill. Well, as they go along, they drop pheromones, which are kind of a deposit that other ants can sense. So what happens is that these other ants basically follow the same paths. Since the lower path is much shorter, automatically you will find that more ants go back and forth along those paths. The same rate, but they just complete the journey faster. As they go along this path, they're dropping more and more pheromones. And pretty soon, what you find is that the scent of the lower path is so much stronger that all the ants are going that way, and the other path is forgotten. So this is how this amazing optimization emerges out of, just no one's actually paying any attention. It's what is called swarm intelligence. Okay, so I think I'm going to basically stop here. I agree that there's always more to do. I think of this as the first bit that I would show my National Science Foundation officer when I've written a grant to tell him that, hey, I'm doing stuff and I need more money to continue to fill in the gaps. Okay, so thank you.
Now the panel can come up here and take their seats.
Okay, is this working? Can you hear me? Great.
Can you? Okay.
Okay, I want to thank you for that very engaging presentation. And I just want to remind you on behalf of the committee that you can take a breath now. I'm sure this is a very nerve-wracking experience.
It is.
We just want to remind you that this is a conversation.
Okay.
Alrighty, so I'm going to begin. You indicated to us, and it's very clear in the book, that you are framing your mathematical creation narrative based on the book of Genesis. And you use the phrase create out of nothing several times over in the book. But as a literature person, I feel that I have to point out that in the book of Genesis, creation does not actually come from nothing. It comes from language. So we hear the phrase, and God said, 9 times in Genesis chapter 1, and each time God speaks, something miraculous appears. So I want to suggest that Genesis 1 draws our attention or demonstrates the power of language, and it's not just any language, but it's actually poetry, because we hear certain phrases repeated again and again. God said, he saw that it was good, it was day and it was evening. Is this sounding familiar to anybody in the room? And so when we get these repeated phrases, essentially what we have are repetition poetics. And in the Bible, repetition marks poetry. Now, you aim to develop language on day 3. You say that solving for X is the closest mathematics gets to language. So my question is this: is there a way in which your creation narrative might recognize and reflect the power ascribed to language in Genesis? And might your mathematical language be framed as a kind of poetry? And if so, how?
Okay, so mathematics has often been compared to something that has intrinsic beauty, and I think the closest mathematicians would come to in terms of looking at math and seeing poetry would be a truly elegant proof. That's something that's a kind of elegance that is hard to really access unless you are a mathematician. In terms of language, what I would say is that, first of all, math is often called a language. Math is just a language. Well, it's not. So I just want to make that clear, that it's a lot more than language. It's actually the ideas. So when we use language, we're really using that to make ideas. I would argue that the same thing is true about Genesis as well. I mean, if you look at how religious texts or myths have developed, I think they have developed to give us more reassurance of how we can comprehend everything and our space and our point and our place within everything, and also get some agency over everything that's going around. And I would say that that maybe is the true metaphor that connects the two. Both math and religion are perhaps trying to get that agency.
Thank you.
You'll get to ask a second question.
Okay, I'm gonna stick with the creation narrative a bit. One of the reasons people think that creating out of nothing happens in the book of Genesis is because of a phrase in verse 2, and I'm reading from the King James Version here. The earth was without form and void, and darkness was upon the face of the deep. So those words, without form and void, are a translation of the Hebrew phrase tohu vavohu. And this is a really odd phrase because it doesn't appear anywhere else in the Hebrew Bible, and it's translated variously. So we get the phrase unformed and void in the King James, but elsewhere it's translated as welter and waste or wild and waste. And so you can see where I'm going here. Welter and waste is not nothing. It's turmoil, it is chaos, it's confusion. And so here again, since you've chosen to model yourself on Genesis, is there a way that your creation narrative can incorporate this welter and waste idea? And what value is it to have your mathematical world create from a kind of chaos? I know you're very proud of the create out of nothing, as it's very close to nothing, it's the empty set, and that's awesome. But what if we bring in this welter and waste idea? What happens to your creation narrative then?
You seem to be a little hostile. I don't know.
No, I mean, this is
a little challenging, let's say.
This is enthusiasm.
Okay. So.
Just wait.
Yes.
That's usually not a good idea to challenge.
Oh yeah, I'm sorry. I take that back. So there's actually a great metaphor in terms of the chaos idea, and that is that if you think about mathematics, there are two theories. One is that mathematics just exists, that it arises out of nothing. The other theory is that we create it, that humans create all of mathematics. The second theory, if we create it, it arises from our brains. Well, brain activity is actually quite chaotic. In fact, the brain is often described as being at the edge of chaos, which is where all sorts of originality and creativity come from. So the fact that you are creating mathematics out of this chaos in your mind is, I think, a nice metaphor in terms of what you're saying about the Genesis idea of creating out of chaos.
I love that, actually.
Yeah.
Thank you very much.
Okay, my turn. Yes, okay. Is this better?
I think
Yeah.
this
One
one over
minute,
here.
yeah. Is that better? Okay, I'll just come a little closer.
Yeah,
Yeah.
I had to really put my face right there.
Okay. So I just wanted to preface my remark or my questions by saying that reading Manil's book reminded me again about, I'm an art historian, and reminded me again as how much artists do use math. And there's been a lot of research on, different aspects of how artists have used math. I mean, just if you think of the way, the art and architecture of Islam abounds in these, amazing use of geometry and repetition, symmetry that Manil talked about to create, these incredibly beautiful worlds, the use of textile art and the way people have used quilts and other types of textiles to create art. But my area of expertise is more in modern art. And so I'm going to stick with that area in asking Manil questions. So in day 2, Manil, you talk about Euclid and Euclid's Elements that was written about 300 BC, about how that was like basically led to the creation of geometry, and it was just very important to math. In visual art, in modern visual art, there was similarly 3 very influential written works by in the 20th century by artists that guided the creation of modern Western art, especially abstract art. Manil made reference to Point and Line to Plane by Vasily Kandinsky, the Russian. There was another really important treatise called General Principles of Neoplasticism or the New Art by Piet Mondrian, a Dutchman. And then notebooks by the Swiss-German artist Paul Klee. So these were really important to the formation of what we call abstract art. And when they approached the blank canvas, these artists were conscious that the marks that they were making were not reflecting the natural world or anything that they had learned, but they were rather inventing something that was not yet in existence, neither in the mind or in the visual world. And as Paul Klee famously said, art does not render the visual world, the visible world, but rather it makes visible. And Mondrian said, I don't want pictures. I want to find things out. And Kandinsky, he took inspiration from the art of children to rid his mind of all learned knowledge about art. So what these artists were attempting was hugely challenging. And so that reminded me of, Manil's subtitle of your book, How to Build the Universe Using Only Math. So how is what you are doing similar to and different from these artists?
So that's, and I put up the 3 pictures that you asked me to. So I think there is a similarity and also a difference. Similarity is Kandinsky in particular has these basic elemental forms, and you find that in Mondrian too, and other artists like Miro, for example. And then you are composing pictures out of these elementary forms in some sense. You're talking about points and lines, and Mondrian and all these artists have very particular rules that they always follow, for example. So this is a very axiomatic structure. You're coming up with some assumptions, you're playing this game, you're expressing these things in a new way. The difference, though, is that, and mathematicians are doing the same. I think one of the differences is that math is so precise that all mathematicians should be able to understand what is being conveyed in terms of actual, it's not like artists are trying to give a feeling. They're trying to express themselves. Math has a much more cut and dry method where anyone can, if they examine your proof or what you're saying, can understand it. Art has a big problem with that. It's just harder. So because it's more felt and so on. Kandinsky, for example, he came up with rules where he polled a whole bunch of people and he assigned colors to different, like triangle was blue and square was red and so on. And he said that is the natural way that we perceive these things. Well, people did experiments in the 70s or 80s and found that just wasn't right. Empirically, that doesn't work. Mondrian, for example, I think you might have read that article in the New York Times recently. One of his paintings might have been hanging upside down. So it just shows, if you have a theorem that's incorrect, I'd be able to correct it at once. Can't do the same thing with art.
Okay. Well, I could go on. And
We don't have that much time.
But yeah, there are some things I don't quite agree with there, but nevertheless, let's move on to my second question. I feel so tempted to,
you have to go on, Praminda. You have to.
So now moving from Euclid to non-Euclidean geometries. That's also something that Manil talks about in the day 2. And he says that, basically, non-Euclidean geometries, for some artists, evokes the otherworldly, and others have been attracted to it because it kind of challenges the assumed truths about our world. And so artists have used many different techniques in their arsenal to evoke the fourth dimension. That includes using shadows, mirrors, fusing multiple viewpoints, making the 2D canvas into a 3D form, or creating voids in sculpture, introducing motion, using gaseous materials. And this is, and of course, computers have really expanded the tools that artists have used. This is by an American artist, Tony Robbin. And he goes on and says, why mathematicians have artists are not like mathematicians who are trying to solve a problem per se, but they are rather more interested in their subjective experience. But he does go on and say that in the development of new metaphors for space, artists, physicists, and mathematicians are in fact usually in step. So my question for you is, can you expand on your project of gaining, and as you term the fourth dimension, glimpses of the beast? How is that? Can that be enabled by a collaboration of artists, physicists, and mathematicians?
Well, I think there's certainly things we can do, and some of this art that we could talk at length about. For example, Dali's idea of trying to show what a 4-dimensional cube would look like. If you opened it up, it would have exactly 8 faces, just like a cube, a 3-dimensional cube has 6 faces. So there are wonderful things that artists have done, and computer people and so on can enhance that. Here is the thing, though. I think for mathematicians, this is very interesting, but the true goal is not to worry so much about the 4th dimension, about trying to visualize the 4th dimension, because we just say, hey, we're not in the 4th dimension. And if you really want to think, here's my dirty secret. When I am asked to think about 4 dimensions, I just think of 3 dimensions. Ask me how to think about 5 dimensions, I'll think of 3 dimensions. Basically, the reason is that in math, you just come up with so many problems that have multiple dimensions. And you have to talk about 6-dimensional things, 7-dimensional things, 20-dimensional things. And you can't expect to hope to really be able to visualize all this. So the key is just think of it as a coordinate system, for instance, and abstract it. It just becomes much easier to deal with. But this is, again, interesting. So thank you.
Yeah, I would say, just to sum up, I would say that maybe one difference I'm hearing is there's a lot more subjectivity and symbolism in art and humanities,
right,
that
sure.
you seem to be not rejecting.
Well, we can get into that. I'm not rejecting anything, but in the interest of time, we will continue this conversation.
Okay, I think I'm next. But by the way, I just want to tell you that since I'm provost on this panel, I'm here to ensure all full academic policies are followed tonight. But thank you, Manil, and thank you for the book. But I do have some questions, and I think, like a lot of work, like a lot of research, the concepts are really thought-provoking. And so I wanted to ask you about one which came out of your book, but you sort of also flowed through your presentation tonight. We saw right at the beginning the concept of an empty set. I think in the book and throughout your presentation, you use the words empty space and nothing, which of course, if you split it apart, means no thing. And I'll also point out, a sort of quote here, some physicist made, not me, that space is not a thing. So in your book, you describe a particular sort of example of this, of trying to think this idea of what is empty space, what is nothing. And I wonder whether you would sort of like to elaborate on it a little bit. And the example you gave, and I think you can probably give it better than me, was actually the Big Bang itself. And the concept in the Big Bang as many of you know, is that in some sense, right at the beginning of the Big Bang, the start, matter and energy in the universe was concentrated at, say, a single point called singularity. And then there was the Big Bang, the matter energy expanded outwards. And so, as you remark in the book, sometimes physicists will say that as the universe expanded, it created the space at the same time. So the space, the creation of space, actually sort of maps the actual expansion of matter. But you also point out that there's another alternative view of this, which is not your view, which there was this huge amount of empty space. Let's suppose it's infinite, it exists. There was a point in there, and then the universe, when it expanded out after the Big Bang, expanded into what you would call a pre-existing empty space. So the space was there as the Big Bang occurred. It wasn't created by the Big Bang. And I think this is really conceptually interesting. I don't think there's an answer, but you have a point of view from a mathematical point of view of maybe what the interpretation might be, or how the difference is, or what the difference is between how, say, a physicist or anyone else might think about that, and a mathematician.
I think, Philip, you've answered your question. I mean, I'm not sure what else I can add to that, just in terms of, you've given such a beautiful explanation. Throughout this book, I will say that I really had to look and try to assimilate what physicists say about all these things. The religion part was easier because in religious texts, you never really talk about empty space. That's sort of assumed. There's already a stage there somehow of locations, points, whatever, and God can create things and just put them on display. In physics, as you said, there's this idea that space was created in order to be able to differentiate between things. Space actually is maybe even a construct that is basically there to separate things. That space and time maybe are still expanding. And so even if it will eventually maybe get infinite, maybe it's finite right now. And then there are other parts of physics that are even more, not exotic, but they talk about space being continuous up to a point, like Planck's constant, and then becoming quantized, just in becoming discrete, and time doing the same. So one of the fascinating things is that in physics, there are all these theories that come up, and physicists basically battle it out. And the theory that best supports the observations, that's what wins. And mathematicians, on the other hand, start with these assumptions and then build things up. And so there's less chance of these alternative views. So one of the most exotic things that I thought was amazing was that space, in some papers I read in physics, that first of all, that the universe is started as 1D, went to 2D, now it's in 3D, and is currently trying to grow a fourth space dimension. Another thing was that maybe we are in 3D, but maybe it is some sort of block in 4 dimensions, and we are just a facet, a face of it. So I find all this fascinating. But yeah.
Yeah, thank you, Manil. I think you've been very generous in saying I answered my own question.
Yes, you did.
But I don't think I did, because I'm still trying to figure out what the answer is.
Okay.
And it's just not from you now, but I think when we just a comment, when we think about, okay, did the universe expand into an existing space, or did it create the spaces going on? And the question that's always in my mind is, how would you tell the difference? I mean, what sort of measurement could you do that would actually distinguish between those two things? And
I wonder if, to answer that part, I wonder if it is the time dimension, because in the way that I'm presenting it in this book, the time is just another dimension which isn't really intertwined in the same way that physicists would say it is. So you have the space, and then this is kind of the way that Newton might have looked at space, that it's a series of instants of the universe, and we're just seeing this series of instants. So
Yeah, and I think that's sort of interesting because I think it illustrates or something that I think is quite important is that, whether it's mathematics or physics, there is a boundary to what we can know.
Right.
You might argue that the answer to the question has to come from religion or philosophy or art, humanities or whatever it is. And I think I just find that really interesting that there is this boundary between what we think of as science and unanswerable questions which can't be answered by science or mathematics. Do I have time for my second question? What do you think?
Well, it's 2 minutes to 6:45.
Okay, so why don't I pass my second question?
Okay, sure.
Okay, I want to go back to the idea of studying mathematics as the study of patterns from an axiomatic perspective. And I would argue that your book, basically the premise of the whole thing is the study of math from a patterns perspective, because that's how you built the numbers. That's how you built the geometry. Yet if we were to ask all the students here tonight what math was, they would probably say it was taking a derivative or integrating something or solving a differential equation. And it's very calculational and algorithmic in nature, and probably maybe not the study of patterns. So how can you reconcile these two views of mathematics using your book?
So I think that was one of the things that I wanted to show, that there is more beyond calculation, that you're doing calculation to understand things. So when you talk about differential equations, for example, there are the types of equations that, starting from Turing and going on to other people, they modeled how you get patterns, and you can actually show how patterns on animals come up through differential equations. So think of math as being the idea part, which you can perhaps say in words and explain through pictures and examples and so on. And that's kind of very interesting, especially to people who might not be mathematicians. And then think about the other part of mathematics, where you're trying to make predictions, where you're trying to really come up with formulas that will, somebody else can use and come up with these patterns or come up with these calculations. And that requires more expertise. So that's the part that, you would have to really pursue it to reach that. I should point out that in schools, often there's a lot of emphasis on drill, your multiplication tables and your division and subtraction and addition. And all of that is very important, because if you know your multiplication and you're really comfortable with it, that frees up your mind to, perhaps be able to digest other more difficult aspects of math. But the problem is that many people just see that picture.
So I think I'm going to maybe skip my second question, which is sort of metaphysical in nature, and jump right to my last question, which is, have you heard from the Pope?
Good point. And I actually have that saved up. So I did send this book to the Pope, and didn't hear anything for a while, and then ended up with this. And this is a letter from, not the Pope, but saying that His Holiness Pope Francis has received your letter and your book and has asked me to thank you. He appreciates the sentiment which prompted you to share your work with him, assuring you of a remembrance in His Holiness's prayers. Wow. I am yours sincerely. And so, he's a character in my book, so I was very thrilled to get this, rather than a note from his lawyer. Okay, I can see Praminda has pulled out a prop, so we have to do that.
Okay,
This is, and if you can't see this, I will just, this is the Romanesco. We were talking about patterns, and I think your question.
Yeah, so my
with
question was
that
nature's always messing around with mathematical patterns, but is this really true? Are fractals in math and nature different? my Romanesco broccoli
Right.
says that they're the same.
Okay, and I should just, point out, if you look carefully at that Romanesco broccoli, there's a fascinating way that it comes about involving, they're actually cells that were trying to turn into buds, into flowers and fail. And then what happens is that other cells start, since they fail, they become stems. They do stem growth rather than flower growth. And then other points start doing the same. And so you get these layerings. You get most of these have 7 layers. So if you look at the pattern, the overall pattern, and then each smaller mountain, and then on the mountain they have little mountains, and on the little mountains they have. So there's actually at least 7 layers of that. But there aren't infinite layers. Mathematicians would want an infinite number of layers. So that's one thing. And the other thing is that there's always a little, look at the way it's turning to the right a little bit. So there's some sort of randomness that goes in, and so it won't quite be as perfect as a mathematical fractal. That said, I want to conclude by telling you, Praminda, if people aren't handling this too much, you can still eat this. And the way to do it is to cut it into slices and grill it with a little olive oil. And what happens is all these little fractal bits, they get completely crisp. And it's just delicious because you get the crispness and the softness inside. So that's...
I want my Romanesco back.
Okay, so that's... what should we do?
Can I go with any questions from the
I
audience?
think it's already 7:50, so maybe 6:50.
I
Yeah.
have a question.
Okay.
How do you address Gödel's incompleteness theorem during machine holding problems and those issues that deal with concepts that cannot be grasped by this process of logical thought?
Absolutely, that's a great question, and this is actually
The second question is,
one question.
Feasible to NP or not?
Okay.
Understood.
So one question about Gödel's incompleteness theorem, and this is actually in the book in the last chapter. And the metaphor that I get from that is that here is mathematics, which is the theorem talks about how it's impossible in the realm of mathematics to prove every statement that can be actually stated using that realm. And this is kind of interesting. Here is the most amazing endeavor of humankind, the highest perhaps some would say. And even that has these questions that you cannot really prove yes or no. What does that tell us about other fields, even about religion perhaps, that maybe we shouldn't really expect all answers from any one field? So that's the way I would kind of interpret it. I see Sam has his hand furiously up, as do many other people.
Yes, I'd like to make a suggestion. You've now written a book on creation, the Big Bang. So now it's time to write a book on the Big Crunch.
Okay, well that'll be that's going to be
Gödel's theorem.
yes. So that's going to be my proposal to the NSF. But thank you everyone. So I think you're going to check with the.
Yeah, we're going to check with the panel here.
Okay.
And I think it was a great end to the previous question for someone that's on defense like this, because you just can't know all the answers.
Right.
Right? So it's a beautiful end to that. Anyway, what say ye?
We have
Wanna
to confer.
Oh, yeah.
So are we gonna
At least
pass
make it
him?
look like you thought.
Are we gonna
That won't be.
Feasible to NP or not?
I don't know. It's more computer science. So
Yes.
All right, the panel has spoken. You just barely made. No, you passed. With flying colors.
Thank you.
Now, I'm going to take that that the audience agrees as well.
Yeah.
Right? Anybody want to say they don't agree? Especially students in the class?
There's one hand up there.
We'll see you after class. All right, thank you. This has been phenomenal. Thank you for coming. There are refreshments at the back. Alumni, go see Alex. She's got pencils for you.
And the book signing.
And there's a book signing over here. Do not miss it.